How you guys doing? So this will be a bit of an interesting video today. What I'm going to be doing is reading values off this microcontroller and accelerometer, and I'm going to use that to pick up the vibrations of the 2.2 kilowatt spindle and get the data on that, bring it on the computer, and then visualize it and graph it out and try and make sense of the ranges of the RPM, like what are good ranges for running tools and stuff, what are bad ranges, like where resonance happens, and yeah, just try and get a better understanding of that data. I'm going to go through basically everything, and including the code at the end if you're interested in this stuff and you want to kind of see how the code is broken down to run the stuff yourself, you can do that. But yeah, let's jump into it right now. How you guys doing? So another little crazy video. I have an accelerometer right there attached to the plate where my spindle goes, and I'm recording through controlling LinuxCNC through Python, incremental steps of 25 RPM, and I'm recording the samples coming off the accelerometer on there. It is MPU 6050 3-axis, and yeah, I'm recording the raw data. And yeah, I want to see if there's any kind of weird frequencies or resonance, vibrations. Yeah, I figure I'll record it now because it's going to get louder. It's been going for a bit. It's at 10,000 RPM, and it's recording 200 samples per RPM. And it started at 4,000 RPM, and it's going to go to 24,000 RPM. Not sure how long it's going to go for. I think it's at maybe 11,000 RPM. 12,000 RPM. So it didn't go all the way. It went to 12,000, just over 12,000 RPM. And it just kind of hung there. So I'm not really sure what happened. And what I'll probably do is just... I've changed some of the settings. So I'm going to do 1.5 seconds per increment. And drop the samples 100. Just so it's a little bit faster, and we'll see if it gets any further than that. Okay, I moved the accelerometer, but more importantly the cable, to be further away from the spindle. When I was debugging it, it wasn't giving me any bad samples coming in. Like, the data is pretty clean, but I don't know. Maybe this might help on the higher RPMs anyway, just having less noise in the system. So we'll try it again. Oh, you gotta be kidding me. It was so close. Alright, so I'm not having any luck with this. It keeps on crashing, and every time that happens I lose everything. So I've yet to put anything in this JSON file. Well, yeah, I haven't even written the new one yet. So what I think I'll do is maybe I'll just make it so it saves a JSON file for every 1000 RPM, and then that way if it crashes, which it will, I can then start on, you know, for instance this one, I could start at 21,000 RPM and finish it up. Alright, so it's going to work now. I can feel it. So I'm going to do 25 RPM incremental steps and then 200 samples. And what I'm doing now, if I can scroll down with one hand, for every 1000 RPM I'm going to save out a JSON file just in case. And what I've done is commented out this keyboard interrupt. I have a feeling that this is what is causing me to exit early and then losing everything. So I'm going to just run it like this, and if I have to exit early to fix this, I can hop into LinuxCNC, so zoomed in, and I can just stop the spindle manually. So we'll give it a go and we'll see how it works. That's not good. Hey, it's the next day, and we have it all finished. So yeah, this little bit of tape helped out a lot. And we have them all done. So from 4,000, well 5,000 up there, up to 24,000. And I did afterwards combine them all on my other computer to just put them all into one JSON file. And there was a fourth value that was not supposed to be there on the accelerometer, so that was removed as well. And yeah, now I'm at the point where gotta start seeing what I can do with the data. Probably thinking of just graphing out the magnitude of per axis, and then see if there's anything interesting in showing with that data, and yeah, we'll go from there. So it is another day, and ran some tests with the data coming off of this, and I've been getting some promising results. What I'm going to do now for improving the data is I'm going to rotate the sensor on 45 degrees, because the MPU 6050, the accelerometer, the IMU in this thing, the accelerometer that is picking up gravity, which is 9.8 going down, I'm getting a lot more resolution on that axis, whereas the other two that are just free floating, they're not picking up a lot of good data. So what I'm going to do is rotate this thing 45, and that'll get me two axes. So right now, let me see if I can poke at something so I can show what the chip is. So if we look up closely here, so right here, that's the MPU 6050. This is a barometer, and I'm not even sure what that one is. And so what we need to do is, currently on the data, the x-axis when it's oriented like this is the vertical, and that's the one picking up gravity. The y-axis I think is this way, because generally z is up when its chip is on the ground. So I'm not going to really worry about z, but x and y I should be able to get pretty decent data with those two axes. And other than that, I'm going to reduce the stepping for the RPM. Right now it's at 25 RPM per step. I'm going to go down to 10 RPM, and also drop the time delay from 1 second to half a second to settle, because 10 RPM increments is basically nothing. Like, the spindle's not going to get any time. And I'm also going to be, I might try doubling. I might go to 500 subsamples. Right now I'm doing 200, but 500 should get me a lot more freedom to work with, and it should just clean up a lot better. So I'll try that. And the reduction of time, reducing the delay from 1 second to half a second, should make all the extra stepping and stuff quite negligible in terms of how long it takes to run. Other than that, in the code, here's the main loop currently. I am picking up a fourth value on the accelerometer, so I gotta find out where that is. I'll probably just get the float values here and just get the first three, and I might do some checking to see if it's a number or not, because I'm finding that I'm getting some issues on the other side where I start to combine all this stuff on the other computer. Another thing I'm going to do is, you'll see I have a clamp here. I'm going to take that off, and I'm going to glue the 3D printed housing to the plate there, and that should just keep it much better attached, and I won't get any possible resonance by this thing only being clamped on one side. And also the clamp itself is probably going to be impacting the resonance on the accelerometer, so if I can reduce all that, that should help. Okay, so I got the super glue on the back. I might have gone a little overboard on the super glue, so that sensor might be on there for good. Might be a permanent inclusion to this whole monstrosity. And as this thing's drying, I'm just going to go over the code and just try and fix some of the little bugs I found on it. Alright, just doing a little pre-flight test. Seems everything's working. That should be dry enough now. And all I really did was just change it here. So I'm just grabbing the first three and just catching that an exception. If there's less values, then it's going to error out, and if there's more values, well, it's just not going to take them. In the previous ones, I was finding that sometimes I would have only 2 values that would show up on the JSON files, or sometimes I had as much as 6. But like 99% of the time, it was the correct values all the time. This will just make sure that it's always perfect. And yeah, I'm just checking right now. I'm saving every 100, but I'm going to change that to maybe 500 because I'm going to be doing steps of 10 RPM. You can hear it going right now doing 10 RPM changes. And you see here that it's just catching some sample issues that is going in. So it's, you know, like for instance there. So yeah, I think we're ready to run this. It's probably going to take a while, but should be good. And if I scroll up, yeah, I can scroll up. Yeah, so there's my settings. So I'm gonna start at 2000 RPM. I think I started at 4000 before, so may as well just go lower. I don't think it's gonna pick anything up. And 10 RPM steps, number of samples is gonna go up to 500. I was doing 200 before, but it wouldn't hurt to get more data. And because I'm doing steps of 10 RPM, I don't have to wait so long for the spindle to get up to speed between each RPM change. So I'm only waiting half a second now. And then the combo of that with, like, even if it, for whatever reason, kind of has a hiccup and starts capturing samples before the spindle is up to speed, I'm capturing so much of it that it won't really pick up the way I'm doing it with by getting it by basically the amount of like values. So like if it's oscillating at, let's say, a value of 0.1, well, 0.1 is gonna be oscillating, and then maybe like negative 0.1 is probably like the opposite one. So I'm gonna be capturing those in order of their hierarchy in the samples and then throwing out the outliers. So changes like that will probably be an outlier, so it shouldn't be too much of an issue. So yeah, I'll stop here and start the recording of the final thing. I'm just letting the spindle warm up a bit and just run for a little while before I do the long test. And if you guys want to know how these MIM sensors are, like what's going on inside of them and how they work, Brick and Tap's got a good video on this stuff. There's the name of it, check it out. And yeah, he even built a, let's see if I can, yeah, I got internet in the garage. Yeah, so like he's even built one, so you can see exactly like all the components and stuff, and yeah, it really makes a lot of sense when you visualize it this way. So I'm gonna run the test now, and we'll see what we get. And last thing before it goes, I will get the code for this onto GitHub somewhere, and probably try and clean up a little bit. It works by remotely controlling LinuxCNC. So I have LinuxCNC open here, and what it does is the Python script will send commands to LinuxCNC, and I'm driving everything through MDI mode, so all the commands kind of go in that way. They don't show up here though. So that's how it works. I don't know if you could get this thing set up with Gerbil HAL, maybe, I don't know. But if you want to do something like this and you're running LinuxCNC on your machine, this would probably just work out of the box. The only thing you'd probably have to change is the USB port for the sensor. You might have your VFD, which down here in my case, over here, so I have my VFD going into the computer. Start on the camera. So I got my VFD hooked up onto the computer over there over USB, and yeah, you just have to make sure that the ports and everything are matching up and not talking cross communication. It's going. It's gonna take a while though. I think it's at 8,000 or 9,000 RPM. Yeah, so just almost 9,000. It's been going for a while. You can see all the JSON files coming in, so every 500 RPM changes. And so far, looking good. I noticed, I'll probably show it, I don't know, we'll see how I edit this video, but between 10 or 11 to maybe 11 to 13,000 RPM, maybe 10 to 13,000 RPM, I get a big spike, and you'll see that in the data. And this one should show even better because I'm probably going to omit the z-axis on the accelerometer. The z-axis would be coming out in depth this way, whereas X and Y, X I believe is going to be going that way, and then Y will be going that way. So because they both have a gravity load on them, 9.8 gravity, the resolution of those should be a lot better, I find when there's a load on it. The quality of the data was a lot better. So yeah, gonna keep on running this for a while, probably an hour, maybe more in total, and we can check it out. Okay, we're almost done. It's been running for a while. This is at 19,000. Oh yeah, 20,000. So, and I can talk still, but yeah, when it was running at around 12,000, 11,000, it was really loud. Up until now, after this, until it gets to 24,000, it's gonna start getting loud again. In the house, and it just finished up. I could hear it stop. So see what it looks like. I'm gonna just disconnect everything. And if we jump back into Linux, I'm going to go home. And we can stop that. And I think I still have this open. So 25, it's so it started at 313, and the last one was 430. So just over an hour to run all the samples. And what I will do now is I'm gonna send that over onto my other computer, and that's where I do all the processing of the data. Files are uploaded into Google Drive, and I'll just peer into here, and it looks like we're getting about, so that'll be X, Y, Z, and then X and Y, it looks like we're getting around 7 Gs and negative 6 Gs. So that should give us pretty good data. And let's see if we go to very lowest ones. So you'll see it's going to be, all the values are going to be ranging around there. And we only get to 2 decimal points, but with all these samples, it's the data improves quite a lot. So if we go to maybe something maybe around 3K. So this is where it gets the most noisy. So you can see the values like 7.8, 743, 72, 759. So they are jumping around quite a bit, and we should be able to see that when it's all graphed out. And this spindle is the 2.2 kilowatt giant spindle. This one is running at 220 volts. All right, back on the computer, and I'll show you what we got so far. This is the second iteration, and here is the matplot lid graph. Working with this library is a real pain in the butt. It's yeah, difficult. So like I couldn't get everything the way I wanted to, but yeah, I think it'll be fine for now. So the top here is the x-axis, and this one is taking basically, well, these two right here, it's basically taking the raw data and just plotting it into a NumPy like grid space, like a two-dimensional image. And then what I do after that is I normalize the values for every RPM step, and I normalize them in the vertical, so that way we can get these nice this nice color transition where if we take like a single slice of this, let's see if I can zoom in with this one. So if I take a little section here, so like each one of these columns is all of the values, so 500 values added on top of each other, and then what we do is we basically normalize that column out, and then that way we can get a nice transition of like the heat map. Let me reset. Okay, let me restart this whole thing. So there are some artifacts that we can see. Like there is these lines here. I think this is an artifact within the accelerometers, and because it's Yeah, like it doesn't, it looks like no matter how many subsamples we're adding in there, it's is always there. And what I would expect with this, the way it's, way I'm taking the values from the accelerometer, so this is with 500 subsamples for a column. If I were to give it like 10,000 subsamples, I would expect that the results of this would be a nice gradient, like a nice Gaussian distribution of all the values, and it won't be so noisy like this. But it looks like this apparent stepping of within the accelerometer. This might be the ADC, the analog digital converter in the accelerometer, or it could be some kind of mechanical property. I don't think it's anything within the code that I'm doing, because these two are just literally just plotting the raw values, so we can see other artifacts such as this. And that brings up some other things. So like this has a bit of drift in it, so we can when I'm aligning this stuff, I get the first set of RPM at 2000 RPM, and I find the midpoint, and then I align and center that way. But that point kind of drifts around it, especially over here. Like we can see, it looks like it dips down, and it doesn't do it on just one step. It kind of, it does it within a range of like, yeah, like maybe 100 RPM or so, and same here, it kind of has little blips and stuff. So yeah, I'm not really sure what's going on there. This is the X and Y axes. I didn't show the Z axes because that one didn't have the gravity load, so its resolution is really, really bad. But that one, like the idle up until around 8,000 RPM, it kind of drifts all around, and yeah, it's just kind of unusable. This bottom graph, I'm basically just taking the values. I'm running some filtering to clean it up, and then I'm taking the modulus, I think it's called, of the maximum values. So for instance, on this red and black portion of that, I'm taking the magnitude of that and then plotting them here, and then I'm using a final filter to average them together to get this red one here. And yeah, I did this one first, and then when I ran it with the 3.3 million samples I then decided I'm going to try and make a heat map like this. So I think they're both quite usable and useful, having them all kind of separately like this. This one kind of really shows that, like, what is the accelerometer picking up on the two axes, and then this one is more of an attempt to blend them together. Starting out by working with this bottom graph here, some of these things didn't make much sense. Like for instance, why on the very lowest RPMs was it showing a value, but then it was dipping down and such, and some of the noise over here, like why was it happening over there? But it becomes more apparent when you look at the raw values, because up until around 8,000 RPM, it does stay very, very low in terms of the magnitude of what the accelerometers are picking up, but it is kind of drifting a bit, and then that's why it's kind of like, if you imagine this is kind of like taking these and then folding them in half and then plotting them in that way, and that's why we kind of see this artifact right here, because it's kind of, because it wasn't in the center, whereas over here we came more of into the center. If I were to spend more time on this, I think what I would do is, when I'm building out this bottom graph here, I would take each column and try and find the center point, and then that way I would have the center point of that match up here, and then that way areas here where it's drifting, it won't matter here. Also, like these blips here, you can see how they kind of come down, and like that's a blip there, and over on this one there's a jump there, especially on the y-axis, which is this one. This is the y-axis, so you can see here it just blips down to nothing and it gets clipped off. And then over here, like you can see that it's just totally clipped off the page there. And I think that's just because the values here, where it's kind of where the midpoint is kind of coming out, is different than where the midpoint over here is. So that's something, if this was more of an issue, I probably would have fixed it, but yeah, I think it's kind of such a minor thing. It's, at least in this use case, it's not really worth going that extra effort. For those that are interested in looking at the code, I'll go through that now. But for other people, you could probably just end the video now. So over here, I have a few files, but you know, let's look at the driver here. So this is the Linux driver. This runs on the LinuxCNC machine, which is running LinuxCNC and running the CNC. And so we have a few things. The way we're communicating with LinuxCNC remotely is through this here, and we can send commands through this function right here, and we can get the stats and stuff like that as well. And yeah, we're importing it over here, and in this class we have a method over here for command, and this command basically sends the command that I specify, and then it waits for it to complete. And we scroll down here, the main is running, well, the file is running main here. So that's what this looks like. So we first start off by opening up a serial port. So in Linux, it looks like this. So we're going to get USB 1, and we need to know the baud rate that the microcontroller is looking at, or is running serial on. So that's this. I can jump into that code after. If it's not open, we're just doing a bunch of checks, and here we're kind of specifying some values for the main loop. So in this case, we're going to start at 2000 RPM. We're going to go up by 10 RPM steps, 500 samples. We're going to wait half a second between every step of RPM change. And we initialize by starting the through MDI to LinuxCNC to start the spindle at a given RPM. We manually just wait a bit. Unfortunately, I couldn't find an easy way. I know there is in LinuxCNC. You can they actually give you a dedicated function or method to run the spindle, and there's an option in there to wait for the spindle to get up to speed. I think my configuration with LinuxCNC is just not set up to allow that, so I have to do all these little manual waits. And we do some stuff about the file. We're gonna put in the steps and the samples into the file name. The important bit here is the loop. This is what we're running. So we're doing a while loop, and we're just running it up until 24,000 RPM, and we're adding steps. This probably should be put at the end, because what's happening is we specify 2000 RPM, and then it goes to 2010 RPM instantly, and we're getting that. We probably don't want to do that. That should be at the end. We wait a little sec for it to get up to speed. That's the half a second, and then we work on the samples. So the samples is another while loop, and we do that based on how many samples we want, and we just keep on sampling the USB serial port to keep on getting samples until we reach 500 samples. And so that looks like yeah, so we're receiving it. We got a regular expression in there to spit out the values. We do a bunch of checks in here to see if we're getting enough values. If we're getting less than 3 values, we kind of get out right away. And also we try and in here we try and convert the strings to floats, and we try and get the first 3 values, and we wrap that in exception handling. Just in case something bad happens, it'll just continue, and then it'll try again. And then after that, we append them all. And yeah, after all that, eventually we get down to here where we're every 500 steps of RPM, we save out a JSON file. And I'm just using JSON just because it's just easy to debug and look at, and it's a big, cumbersome, slow format for what we're using for. If I actually open up one of these here, that's what it looks like, and it's just, yeah. So yeah, we're just dumping it there, and eventually we run a M5 command to stop. In the code over here, so in this we're doing a bunch of things. So initially we got to combine all the data. So I have a little function over here which basically just goes through the folders, and we're using glob to get all the files. And for every one of those, we load them up, and then we kind of parse through everything, and then eventually we save a Python pickle at the end. And we do this because the pickle file reads much faster than a big JSON file, and it's much smaller. So with all the iteration that we have to do to write all the rest of this code, we got to run this thing like 100 times or so just to build out the code. If we were loading up a 80 megabyte JSON file, it just would slow everything down a lot more. After that, next thing was we would go into main, and here's main here. So we run two things. We run prep data and then graph data based on the file name, and this file name goes back to the pickle file. So prep data, here's the function there, and we're basically loading up, and we kind of store the X and Y images, and we kind of do it that way. This actually runs a build image. That's why this little function looks kind of sparse. And the build image is just a way for us to loop over a whole bunch of steps to build out the image which we see here, this raw stuff. So that takes a bunch of steps in here. This is basically how we build those raw images out. So we have a few things coming in. We got the index. The index is the X, Y, or Z. The index is X, Y, or Z of the accelerometer values that we want to get. So we start out, we got to build out some kind of data, some piece of data that we're going to store everything. So we're going to use a kind of representative of a 2D grid. So we're using NumPy 0. So we build that out with 0 values. Just looking at it, it looks like the values from the accelerometer range close to around 9.8. So what we do is when we convert that to decimal point value, raw values from the accelerometer, because they're only giving us, you can see here, only to do 2 decimal points. What we do is we convert that value into a position on the grid, and we can see that down here. So this is just to hold everything, and then we first want to get the first step and get the average. So this little chunk here is basically to find the 0 point value, and this just helps us kind of align everything after. And this is just getting the first RPM, and then just getting all of the subsamples for that RPM, and then just averaging them out. Over here, we're looping through all of the RPMs and then all of the samples, and then we are converting the sample value to an integer, and we're also getting the RPM step. We're doing a little bit of math in here because we're working with like from values from 2000 to 24,000, but we don't want to have those that number of size of our Python structure. So instead, what we do is we divide that down, because we're only doing 10 RPM changes. So then that way every single every single column represents a change of 10 RPM. And this 200 is in there because we want to offset everything by 2000 RPM. So we do it by 200 because we're dividing this over here. And then we basically just take whatever value that is in that grid, and then we add 1 to it. And we do that over time, and this builds up the values. So if we go back to over here, So over here, a lot of the values in the beginning, they're probably within like maybe 10 separate values or so. So it builds up to a very high number there. Whereas over here, due to the fact that the accelerometer is kind of acting like a pendulum, where most of the time it's going to be around here, and then as it swings, it's going to be more sparse in terms of the points that we pick up over there, and then it's going to be more over there. And so that's how we're doing that. And after that, this is the portion where we're slicing it, and then we're finding the min and max and the average, and we're just trying to normalize that column. And then that basically is our NumPy raw representation of that image. If we go back over here, so we're in prep data. So those are the two images we build out, and then over here is just some slicing to. This is just basically, these are just kind of hyperparameters to just as we present the raw data, we want to kind of just slice it up so we can fit it nicely. Let me go back here. So we want to, it's just to kind of clip everything off so we don't want to have all this empty data everywhere on the tops and bottoms. So that's the purpose of that. And graphing data, let me just check. Yeah, so we're in graphing data. So we got our two images, and then this one here is just kind of lobbed on at the end, graph final. That one represents this one here on the bottom because I did this one first and I did these two second. And I didn't want to try and combine this graph final, which is over here. I didn't want to combine it into this building of the images, even though some of it is kind of similar. And yeah, this one is just, yeah, it's not that nicely organized. It could be cleaned up quite a lot, but similar kind of thing. The main differences with this is we're using mode to find the maximum value per a given RPM step, and before we do that, we do some cleanup with rejecting some of the outliers with this little function here. And yeah, we're sorting it down there, and we running absolute, so we're flipping in case so like we're getting the maximum values basically, but the maximum could either be somewhere over here or it could be a negative number somewhere down there. And what we want to do, well, actually when it's like that, this is not a positive and this is not a negative because there's gravity load applied to everything. So this chunk of, where do we go? Yeah, so this little chunk over here is we're kind of just averaging it so we can put it back into that range again. After that, we're running a little bit of filtering to clean up a bunch more of the noise and some more normalizing steps, and then this A value here represents the average of the red here when we're combining it, and we do a little bit more filtering on top of that one, and that gives us all the data for that. Then we return the RPM, the X, the Y, and then the average of it, and then we plot those out. And so we're basically there. The rest of here is just NumPy stuff. So we're doing subplots. So we do the first x-axis, which is this one on the top, and we're doing the im show. I guess this is image show, and we're interpolating it. This is the color map. We're using the one called jet. X and Y are basically the same. We got some junk in here to try and clean up the ticks and stuff, and same over here. The combined one over here is similar kind of deal, except we're using just a regular plot right here. So we plot out the X, the Y, and then the average. We fill the in-between of the average just so it's more pronounced in the image, so it's all red there. And then we apply a grid onto it. we add a legend, and that's basically it. That gets us the code. And let me just jump over here. Yeah, so this here, this is what runs onto the ESP32. So this is like an Arduino, basically. And all this is really doing is it's using an existing library to read the MPU 6050 and using the wire module to run serial back to the computer. And yeah, that's basically all this code. It's I haven't really looked too much into how all this stuff works, but we're just building out a something to write to the serial. Looks like it's over here. So serial print. So we got the acceleration of x, y, to z, and that's basically what comes back over the serial, and that's what we're cleaning up and filtering out over here with this regular expression. If I had more time, I might try and make the code what's spitting out here a little simpler to deal with the regular expression, but it is what it is right now. So that's basically how all the code works. It's I'm sure it could be done a lot better. If you're doing something like this, you could use this as kind of like a baseline to reference things off of, but I'm sure there's a lot more things that could be improved. If I go back to the graphs here, it could be nice to have some functionality into this, where maybe this is built into like a PySide application, and we could have options where, for instance, the raw data, we could show like raw or adjusted. So like we could try and find like the 0 value and then shift every single one of these columns of data so it's perfectly aligned down the center, and just try and remove all the drift. So it could be useful for stuff like this, stuff over here, and then the drifting in the beginning. This one here especially is quite interesting, and let me zoom into both of those. Like, yeah, like I don't know exactly what this is going on here. Like, it looks, I don't know if this is an artifact or if this is something real in the data. This could be the accelerometer self-resonating at around 17,000 RPM, and we're kind of getting this like standing wave kind of effect, maybe over here as well. It's possible that's what that stuff is. But yeah, there's a lot of stuff, and that all kind of goes back down to here when we're combining it. If I reset this thing, shifting everything over would then help with the averaging portion. Whoop. Up down here, and this would be a lot cleaner, and all of this would probably be a lot less noisy. So yeah, that's where I am with this. I don't think I'm going to spend much time anymore on vibration testing with the spindle. It's kind of like, my intuition was that around 10 to 13,000 RPM, it seemed like it wasn't a good RPM range for the 2.2 kilowatt spindle, at least set up on my machine. So this kind of really just shows that out quite well, where like at least around, like, it seems like I don't have any vibration up to around 8,000 RPM, and then it gradually kind of picks up, but it around 2,000 RPM, it picks up quite a lot over here. Yeah, this chart's easy to see. So we get a bunch, but like this area right here is like from 12 to maybe 14,000 RPM. It's just, you don't want to be there at all. And then over here, like at the higher end range, anything up to maybe 22,000 RPM is pretty good. But once we get into the last 23 to 24,000 RPM, it kind of gets a little bit more noisy again, at least on the x-axis. But yeah, that's the interesting thing, is on the y-axis it actually gets, there's less noise, which is kind of interesting. So yeah, over here it's kind of averaged out, so we can see why x-axis kind of blips up, and then the y is, because of how it is drifting, it is basically a 0 value down there. So yeah, hope you guys thought this was an interesting video, and I will see you guys next time, probably doing actual machining again. I'd like to try out those new end mills that I got for the high feed cutting, which I showed in a previous video that I've never actually run yet. I'm just kind of busy with all kinds of other things. So I'll probably try and get to that stuff next. And yeah, if you guys know anything about signal processing, because I'm not a data scientist. I don't do this stuff for a living. If you guys have any ideas of what I'm kind of seeing here, especially these artifacts, like for instance this one over here, would be nice to know what's going on there. And yeah, I think these lines, horizontal lines, are probably artifacts within the accelerometer and not actual components of the frequencies and the resonance, I don't think, because of how flat they are. But yeah, if you know that, shoot that down in the comments. I'd love to hear, and I will see you guys next time.